Now let's try computing confidence intervals empirically via the method of bootstrapping. It's going to be pretty cool, I think. I'm starting with exactly the same code that I did in the previous code video, so I'm not even going to talk about this. And here we draw random samples. This is also exactly the same code that I used in the previous video. So I'm also not going to talk about this. Okay, here comes the new stuff. We are doing bootstrapping. So here is the number of bootstraps. I'm going to do 1,000 iterations, and I'm going to store all of those means from all those iterations. And here is where the action happens. So what I'm doing is taking my sample data. So I'm not going back to the population and sampling new data from the population. We're only ever working with the sample data that we have already collected from the population. So we take our sample data, our 40 data points, and we're going to randomly sample from them 40 elements. And this true here means that we're sampling with replacement. So let me just illustrate to you what this looks like in a simple example. So I can say ran sample. Let's pretend our data are like 1 to 5, and I'm going to sample 5 of them, and I'm going to sample with replacement. So in this particular case, we got 1, 5, 5, 1, 2. So this is pretty interesting. We randomly sampled from the numbers 1 through 5, integers 1 through 5, and that random sample ended up with 2 1s, 2 5s, a 2, and no 3s and no 4s. So we can run this again, and now we get 2 2s and 2 1s, and no 3 and no 5 and 1 4. So I think you see the idea. So we are drawing the same size, the same sample size. So we're always going to get 40 samples, but there could be some redundancy and there could be some missing values or some data points in sample data that don't get included in this average. So let's see what these, I'll have to run all of this. Let's see what these look like. So I'm just going to say plot boot means, and here is our bootstrap. So that's pretty interesting. The sample mean, the true sample mean from this sample is 15.8. So it's around here somewhere. So this is the actual sample mean. And then all the times, the 1,000 times that we sampled randomly from this population or from this sample, and sampling with replacement, then those get distributed all around here. Even, this one point is probably the highest point here. Maybe this one's the highest point, 26.4, and we got the smallest value of 6.8. So quite a difference. It might be pretty surprising at first. This is the sort of thing that can happen when you are randomly sampling with replacement. Okay, but what we care about is the confidence intervals. So I'm getting the 95th percentile, but we don't actually want just the 95th percentile because we need this to be two-tailed. So this is 2.5%, and this one should be 97.5%. So in total, these two give us the 5% or 95% confidence interval. Okay, and so that happens to be 9.5 up to 23. So that's our confidence interval around the sample mean, which was 15, almost 16. So let's see what this looks like on the graph. So here I'm going to have a new figure. This looks pretty similar to the figure that you saw 2 videos ago in the last coding video. So here is the true mean. Here is the sample mean in red. In this case, again, it happened to work out. It's a bit by chance, but it worked out that these are extremely close. Here's the 95% confidence interval in this green bar. And what we get here that we didn't get when just applying this analytic formula is also the actual distribution of the sample means. Now, I'm sure that you are not even a tiny, tiny bit surprised to see that this distribution of sample means is Gaussian, even though the population, I closed that figure, but even though the population was strongly non-Gaussian distributed. Okay, so the last thing that I want to do is compare the two methods of computing the confidence interval, so empirical and analytic. So we already have the empirical distribution, and here is the analytic confidence interval that, this is just copied and pasted from from 2 videos ago, so I don't need to talk about this. So we find that the empirical confidence intervals go from 9.5 up to almost 23, and the analytic confidence interval, again, it's also 95% confidence interval, goes from 8.5 up to 23. So they're not exactly the same, but they are, I don't know, would you call that pretty close? I guess it's hard to know how to evaluate how close those things are. I suppose you could recompute this empirical confidence interval multiple times to see how it relates to how that distribution over many repeated bootstraps relates to the analytic distribution. Actually, let's do that once just to see. So what I'm going to do is keep all of this stuff the same. I'm not going to generate a new sample. Keeping our sample that we already have, I'm going to compute a new bootstrapped confidence interval and then print that out again. And then let's see. So now I didn't actually write down or remember very well what this was before. Okay, so this was the first time. So I'm going to put that down here. So this was this was the first time we ran it, and this was the second time we ran it. Of course, the analytic confidence intervals are exactly the same. And these confidence intervals are pretty close. They're, in the same range. It goes from, here it went from 9.5 to 23. Here it goes from 9.25 to 23. So we get actually different numbers, different results each time we run the empirical bootstrap method, although they won't be too much different. Okay, so I'm going to get started here with pretty much exactly the same code. So this is literally exactly the same code as 2 videos ago when I created the analytic confidence intervals. So here you see the data distribution. Now some of this code is exactly the same. This code here is also exactly the same as in 2 videos ago. Here is where we start getting some differences. So here is for the empirical bootstrapping method. So we're going to run 1,000 boots. Do you call this 1,000 boots? 1,000 iterations of bootstrapping. And what we do is we randomly sample from our sample data set and then take the mean of that and store the mean. So be careful here. We are not actually drawing new samples from the population. We are only working with the sample that we already have collected up here. And instead, what we're doing is drawing random samples. So that's what this random.choice function does. So we are computing random samples from this sample data, and we are getting 40 of them. So 40 is the same size as sample data. And actually, to make this a little bit more clear, it's important to me that you understand really what this line of code is doing. So I'm going to say insert cell below, and let's do numpy.random.choice. So I'm going to come up with a distribution of 1, 2, 3, 4, 5, just a couple of numbers here. And we're going to draw a sample size of 5. So now let's see what this random sample with replacement ends up being. So here we are randomly sampling with replacement. That's what this choice function does. And notice the population we started with, 1, 2, 3, 4, 5, and what we ended up getting was 2 2s, 2 5s, and 1 4. So we don't have a 1 and we don't have a 3 in here. So we have both redundancies in the data and we are missing some data points. Okay, so we can try this again. And now we got, wow, this is actually pretty unlikely, but this kind of stuff happens in a crazy, wild, random universe. So we got 4 2s and 1 3. Okay, and here, this is also pretty unusual. We get 1, 2, 3, 4, 5. All right, it's a lot of low frequency events happening here. Okay, but I think you get the idea. So we are randomly sampling with replacement from our sample data, the same sample size, and then we compute the mean and we store that, and then we compute the percentile. And we need 2 percentiles. We need the lower bound and the upper bound. The lower bound corresponds to, so we're getting the 95th percent confidence intervals. So we have 100 minus 95, so that gives us 5, and then we divide by 2, because in fact we need 2.5% percentile from the bottom of the distribution, and then 2.5 percentile from the top of the distribution, which actually means 97.5%. Okay, so this is our confidence intervals around the sample mean. Okay, so then we're going to graph all of this. So let me show you what this graph is going to look like. All right, so I ran this code again, and to my absolute horror, the labels here were incorrect, just like they were incorrect in the Python code from 2 videos ago. Now, back then, I was willing to admit my shame and correct the code in front of you. But now I was too embarrassed to do that, so I just edited the video. Now we have all the correct labels. Okay, so we have the true mean, which again, in real data, in the real world, we don't have access to the true mean, but now we do. We have the sample mean from our sample. We have the empirical 95% confidence interval, which is given by this green bar. And what we also get here, which we don't get for the analytic confidence interval computation, is the empirical distribution of the sampling from the sample data. Now you shouldn't be surprised at all to see that this is roughly a Gaussian distribution. And you know why you shouldn't be surprised that this empirical distribution from random sampling is a Gaussian. And if you are surprised, then I don't know, shame on you. You should have been paying more attention when I talked about the central limit theorem in the probability section. Okay, but anyway, so now you can see empirically where this 95% confidence interval actually comes from. It's coming from the 95% of this empirical resampled or bootstrap distribution. So we have 2.5% hanging out on the left and 2.5% hanging out on the right. Okay, and now what I want to do is compare the two formulas, the two methods for obtaining a confidence interval. So we have the analytic formula that you saw in the beginning of this section and the bootstrapping empirical method that you learned here. So all I'm doing is basically just copying and pasting code from the previous Python video. And then we're going to see that the empirical confidence interval is 14.2 up to 29.6, and the analytic confidence interval is about 13 to 29.6. So they are fairly close to each other. They're obviously not identical. These ones are really close. The upper limit is really close. The lower bound is a little bit further away, a bit further apart from each other. Now it's kind of difficult to evaluate how closely the empirical and analytic confidence intervals match here. You could, if you want to, repeat the empirical method many times using the same sample, and then kind of see how closely the distribution of the empirical confidence intervals matches the analytic solution. And so I'm not going to do that here, but what I am going to do is run this through once just for comparison. So I'm going to copy and paste this here, comment this out. I'm going to rerun this code again, this code, but we have to be careful here because I don't want to create a new sample. As soon as I create a new sample, I'm also going to get a different analytic confidence interval. So I want to comment this out so that the sample data are identical, and I'm just doing the bootstrapping again. So run that cell again, get a new bootstrap confidence interval, and then I run this again to print it out. Now, no surprise, the analytic solution is identical. If it weren't, then something would be really bizarre. And so it's interesting to look at the empirical distribution. This was from the first run, and this is from the second run. And you can see they are quite close to each other, but not identical. So that's a demonstration of something I mentioned at the end of the previous video, which is that one feature of empirical confidence intervals via bootstrapping is that you're going to get different results every time you run it.